Yeah, so just to be clear, this is the knitting talk. You have made it to the end of day 2 and you're in the knitting talk. If anyone, I won't be offended if you go, oh crap, and leave. So just to address the elephant in the room then, how many of you here have ever knitted in your life? Oh, heaps. All right, cool, yeah. All right, knitters, if you've got your knitting with you, feel free to whip it out and knit through my talk. All good. For the rest of you muggles, don't worry, no knowledge of knitting is assumed. And I'm not going to teach you either. This is not a knitting class. This is a coding conference, right? So I am going to start off with a 3-part coding quiz. And guess what? There are prizes. So question 1, I'm going to show you a bit of code. You have to tell me what the output is. Okay, ready? So this is a photo that went viral from a cafe. Who knows what the secret discount word of the day is? Ooh, hard one. Just yell it out. What? That's not a word. Oh, this is not going well. Yes, encryption to that man over there. Would you please give him a Kit Kat? Yes, encryption was the word. Oh my God, that went really well, didn't it? All right, so question 2 is a little bit harder. This is going to be some coffee script, and put your arm up when you know what it outputs. Okay, ready? Here it is. What is the output of that? Put your arm up if you got it. Come on, somebody. Surely you know this one. Oh, over there, yes? It is fizz buzz. Can you give me the first, like, you know? All right, that's fizz buzz is close enough. There you go. It's the infamous coding interview question, fizz buzz. All right, so that's what that outputs. Okay, question 3, last question, all right? What is the output when you execute this particular program? Scarf, now I'm a bit more specific. Come on, Bernadette. I can't believe it. The correct answer is, of course, feather and fan stitch. I also would have accepted, of course, old shale. And here, as you all know, is what it looks like. That is a stitch. All right, so you see what I'm getting at here, right? All right, so I'm going to go back to the beginning now and tell the story. So I have actually been working in tech a lot longer than I've been a knitter. So I grew up in the US, obviously from the accent. Yeah, it hasn't gone anywhere. And I worked as a web dev in the UK before I moved to Australia in 2001. And when I got here, waiting for my visa to be approved, there was no Netflix back then. I needed something to do. And I thought, I'll do a craft or something, you know, something offline, something not technical, maybe make something nice for my house. So I did some cross stitch, that was boring. And then I thought, knitting, you know, that can't be too hard. Like grandmas do it, right? So totally offline, totally non-taxing, I can do this. So I got a Kids Learn to Knit book, a ball of wool and some needles, and I started making a pot holder. And that damn thing nearly killed me. I had to pull it apart about 12 times. And by the time I had it done, I had 2 things. I had this super freaking awesome pot holder, which I'm very proud of. And I had the realization that knitting is just code. Like these 2 activities in my mind that were so separate, well, in reality, it was more like this. You know, I was seeing all these similarities between what I was doing in my day job and what I was doing in my hobby. And so that's why I wanted to talk to you about some of these things, because I really, look, this is not something you need in your job. We all recognize that. But I really think that by looking at what you do in a new way, it'll make you better at it. It'll open your mind up and hopefully inspire you a little bit. But before we get started, if you learn nothing else today, let it be this. This, not knitting. This is crochet, okay? Crochet uses a hook. I see where you get confused. It's got a ball of wool and you make something, but it's not knitting. So crochet goes off in any direction at any time, and it's really good for making sort of 3D sculptural pieces. If you're a mathematician, go home tonight and Google crochet maths, and then next year you'll be up here and you'll be talking to Uncle Bob about crocheted hyperbolic geometry. So instead, knitting. This is knitting. So knitting is done with at least 2 needles, sometimes more, and involves the sequential processing of stitches from one needle to the other. So you go all the stitches off one needle onto the other, swap hands, do it again. If you're knitting in the round using a needle with a cable on it, or a set of 4 needles, you're actually knitting around and around in a spiral. Okay, so the first thing I learned when I started making my pot holder was that there are actually only 2 stitches in knitting. knit and purl. So as I know, spoiled this morning in my introduction, knitting is binary. And to a computer geek like us, that gets the brain going. You start thinking, hey, I could use this to encode digital things in lots of different unique ways. And once I started looking for projects like this, they're all over the place. So I can combine knits and purls to make ribbing for a beanie. This here is the decoder hat by Zabit Stewart. It encodes up to 12 characters in ASCII at 8 stitches per character. So of course, the message length, that memory limit is pretty hard here, limited by the thickness of the wool and the size of your own head. Now, if you wanted to encode something longer, you could knit a scarf. So this scarf encodes the binary source code to Ravelry.com, which is basically GitHub for knitters. You are giggling. With knits as the ones and purls as the zeros. So using that scheme, you could encode pretty much anything digital. If you're more of a black hat type, you could even knit a virus. In 2001, a team of activists from the Viral Knitting Project actually knitted the source code to the code red computer virus into a scarf. Soft, fluffy, and deadly. You could wrap it around your neck and walk through any airport in the world. So much for firewalls. Now, maybe like me, you like cables. The hat on the right here represents the numbers from 0 to 15 in binary notation, depending on where the cable crosses occur. And the scarf on the right has a hidden message in binary revealed by cables that look like little ones and zeros. If you prefer color, you could use the width of knitted stripes to encode a character set. So the stripes on this guy's jumper actually spell out the classic first programming exercise. Everyone say it with me. Hello, world. Yes. If you want to get really literal, you can knit zeros and ones into your scarf. So I'm happy to tell you that depending on how tall you are, the average scarf will hold around 120 bytes of information, which, as we all know, just shy of a tweet. And of course, not all information is text. One thing that I learned was in World War II, the Belgian resistance recruited little old ladies who lived near rail yards to watch the German trains and secretly encode their movements into their knitting. She doesn't look so innocent anymore, does she? Here are some more mundane examples. On the right is the scoreboard scarf, which is a record of a sports team's season, with all of their points in one color and all of their opponents in another. I think we all agree we really hope he's barracking for the gray team. And the scarf on the right is a sky scarf, where every row is the color of the sky above the knitter on the day that he or she knitted it. So my last example of encoded and knitted data actually won me a second prize at the Sydney Royal Easter Show a few years back. And ladies and gentlemen, I give you the knitted QR code mitten. Thank you, thank you. It actually does work. It was surprisingly difficult. The first problem was one of resolution, so it's actually knitted on a finer wool. But the fact is that QR codes really need squareness to be recognized, and knitted stitches are inherently rectangular. They're wider than they are tall. So I tried all these different prototypes and methods until I finally hit upon the very technical term, stretch the hell out of it. And that seemed to work. So it actually does scan. I'll bring it down. You can try it after my talk. And it points to a URL on my personal site that has the pattern for the mittens, so they're self-replicating. Okay, so back to my story. So once I had the basic mechanics of knits and purls down, it was time to learn to read patterns. And now every knitting pattern in the world, the first line will look something like this. Cast on 24 stitches. And that means to create that initial row of loops on your needle so that you can start knitting. Now my brain looked at that and read it and immediately thought, well, that's just a for loop, right? It's a control flow structure for specifying iteration, allows, code to be executed repeatedly, usually has a variable or a loop counter of some kind. So in my mind, I turned cast on 24 stitches into a sort of knitting flavored JavaScript. And it's not ES6, so don't even go there, but it might look like this. Okay? So in this example, I would have a variable for my stitch count, and then I just loop through that for loop until I reach the right number of casted on stitches. So another really common use of for loops in knitting is to set out a stitch pattern. Like in that beanie, you might have 2 by 2 ribbing, which in a knitting pattern is usually done with K2P2. That means knit 2 stitches, purl 2 stitches. So again, in my brain, that turns into code. It turns into 2 for loops, one of which that handles the knits and one of which handles the purls. And of course, if you can iterate over stitches, it stands to reason that you can also iterate over rows as well. So a pattern will usually set out a series of rows and then tell you to repeat it a certain number of times. So for example, repeat rows 1 to 4 10 times. Again, in code, I would simply call my 4 next row methods in turn 10 times. So as I poured over that potholder pattern, I realized there was another type of loop lurking. So knitting patterns use phrases like this a lot. Repeat to end of row. And what is that? That's a while loop. It's a control flow statement, again, allowing code to be executed repeatedly based on a given Boolean condition. And in the condition is, have you reached the end of the row yet? If not, keep doing what you're doing. So, very simple. While the expression not at end of row is true, just keep knitting. And another really common while loop usage is, have you gotten it to the desired length yet, which often equates to, am I almost out of wool? So instead of telling you to repeat something a certain number of times, it'll just say, repeat rows 1 to 4 until scarf is 80 inches long or desired length. Okay, cool. So in my mind, I set a variable for the desired length to 80 inches, and then in my while loop, as long as I'm under that number, I just keep repeating my 4 rows. And then once I get to the 80 or whatever the length is, I'm ready for the next instruction. Now, in reality, patterns mix and nest for and while loops of different configurations. So going back to that feather and fan I showed at the beginning, you'll recall, of course, that it included this line. Row 3, star, knit 2 together 4 times, yarn over, knit 1 8 times, knit 2 together 4 times, repeat from star to end. So the sequence is 4 knit 2 togethers, then a nested for loop that repeats yarn over, knit 1 8 times, then another 4 knit 2 togethers, and that keeps repeating as long as the condition you're not at the end of the row is true. Simple, right? So once I finished my potholder and I had the basics down, I was ready to move on to garments. So I picked out a jumper pattern, got all my wool ready, opened it up, and the first thing I see is cast on 242, brackets, 256, 270, 284 stitches. Okay, so if you don't know knitting, those 4 numbers correspond to 4 garment sizes defined at the start of the pattern. So here you can see the measurements for a cardigan. So let's assume I want to knit the 38-inch size, so that's the first number. So then I just need to cast on the number of stitches that correspond to that size. So this is pretty much just a switch statement. It's a control mechanism used to allow the value of a variable or an expression to change via a multi-way branch. So in my head, that cast on instruction might look like this. I set a variable for my particular size, and then based on that, I know how many stitches to cast on, in this case, 242. Now some patterns actually include a lot of sizes, like if they have kids' pack sizes and adult sizes, so you can have really long switch statements. And actually, sometimes it's not just a number that changes. There might be whole sections of the pattern that you use or you don't use for different sizes. So that kind of takes you into the next concept, which is subroutines. So I realized that the more complex a project is, the more likely it was to be broken down into different sections, kind of like subroutines. In programming, that's a sequence of instructions that performs a particular task packaged as a unit, and then you can use that. You can call that subroutine wherever that task needs to be performed, and depending on your language, you might call it a function or a procedure or a method. Well, this is used all over the place in knitting. So if a pattern uses a stitch pattern like that feather and fan, it'll be declared in a separate block at the start of the pattern and then just invoked wherever it's needed. So here's an example where a pattern defines 2 particular stitch patterns, twisted rib and twisted rib in the round. And then in the actual pattern instructions, the twisted rib function is invoked here with the call work in twisted rib. So just to stretch this metaphor as long as we can, if this were a computer program, it would look maybe like this. So I've got a function called twisted rib. You'll note that I pass in the appropriate stitch count, so that I can use it in a for loop to stop 1 stitch before the end of the row, do a final knit or purl before swapping the needles. And I'd invoke it by calling that function wherever needed. Now another way, a way I prefer, because this is getting kind of verbose, a way I prefer declaring subroutines and functions and patterns is with charts. So here are a few examples from a cabled cardigan. So rather than defining those subroutines in words, it uses 3 different charts. You might use one on the front of the cardigan, one on the sleeve, one in the cables. You get the idea. Now the real fun happens when you have a project that uses more than one of these at the same time. And that actually takes us into the realm of coroutines, which are a special class. So subroutines start and finish and don't hold state, but coroutines, they can exit by calling or yielding to other coroutines, and then later come back to the point where they stopped. It's like hitting the pause button. And you can also have multiple instances of them going at any given time. So you see this in knitting with very complicated patterns, and I happen to like a challenge. So last year I started knitting this beast. This is called Morrigan. It's a cabled sweater, and it involves 20 different charts with 56 instances of them going at any given time. This is row 1 of this pattern, row 1, after casting on. Each one of those letters corresponds to an entirely different chart, which vary in length from 2 rows to 66. You could even look at this as a type of interleaved multi-threading, pun very much intended, where the CPU, which in this case is my brain, has to take a new instruction from each thread in turn, and depending on how much RAM I have available, things can grind to a halt. So what I'm saying is this is not the type of pattern you knit at the pub. So once I started seeing code in my knitting, I was seeing it everywhere. Things like Ravelry, which I said was already like GitHub. Doing a count of your stitches at the end of the row is basically a unit test. Running a safety line through a row, that's pretty much doing a git commit. I could go on and on with this stuff, but we need beers. So instead, let's talk a little bit more generally about knitting pattern languages and how they relate to programming languages. So sadly, my imaginary knitter script is not a real thing. There is no worldwide knitting authority body, and there is no agreed upon standard. So much like programming, there are a million different ways to accomplish any task. And the particular form that a pattern designer uses depends on a lot of different criteria. Is it a garment or a scarf? A garment might have a lot of pieces. That would influence the way you wrote the pattern. Are there multiple stitch patterns? What about the medium? Knitting patterns used to be sold on paper and ink, but nowadays you can get PDFs online, so you don't necessarily have to be as concise as you used to be. Also the audience, which type do they prefer? That can vary quite a bit by the level of experience, by their brand affiliation, and even culturally. So it turns out these are very similar to the kind of questions you consider when you're trying to pick a programming language, How well does it handle the particular domain, the level of complexity, the data types and operations that you need? How portable do you need it to be? How readable? And will it run on your intended platform? And how performant will it be? Now here is something interesting, and there is a KitKat in it for you. The history of programming languages actually begins with textiles. It really does. So KitKat to whoever can tell me what this is. There it was, the guy in the plaid shirt right there in the middle. Well done. That is indeed a Jacquard loom, invented by Joseph Marie Jacquard, or Joseph Marie Jacquard, in 1798. And what is on the front of it? Punch cards. We had them first. So Joseph Marie Jacquard developed a system that would allow punch cards to manipulate and control the series of operations that this loom would carry out. 40 years later, Charles Babbage wrote of using this mechanism to input programs and data into his proposed analytical engine. Yeah, knitters. So have a look at those punch cards, and then look at this modern knitting stitch chart. Ready? Pretty similar. So when executed, this chart creates a pattern called moss stitch. So the blank squares are a knit stitch, and the dot is a purl stitch. So this is effectively binary. This, my friends, is the knitting equivalent of machine code of a first-generation programming language. There's no compiler or assembler needed. It's very easy for the CPU, which in this case is my brain, to execute, See a blank square, I knit, I move to the next stop. I see a dot, I purl, I move to the next square. Get to the end of the row, swap the needles, do it all over again. So here's another binary example. This one's from 1935. It's a checkerboard design. I'm actually knitting this one. And in this case, it doesn't use symbols. It uses colors, black and white, to show the color of the thread that you're meant to use. So this is really useful for complex multicolored designs because it provides a means of error checking. At any point, I want to run a quick smoke test. I can hold up my knitting to the picture and see if it looks like the picture. It also saves a lot of space. We're talking about data compression here. Like if this series of steps were written out, each of those rows in full in text, it would take up a lot more paper and ink. And I know that because this particular pattern includes it. Pages and pages and pages. So as patterns got more complicated, publishers realized they could save space by using charts, and that they could provide even more information by using more than 2 symbols. So here's an example from the 50s, and this uses 5 different typographic symbols to represent different instructions. So we've got an additional level of abstraction here. This is sort of like the mnemonics of an assembly or a second-generation programming language. You know, I can read it, but to actually knit it, I kind of have to translate those symbols into the appropriate actual actions. So the Roman numeral 2 in this example means to knit 2 yarn overs, which are sort of like holes. And the 3 is a method to reduce 3 stitches down to 1. Now, some of you knitters are probably noticing these symbols, you've probably never seen them used this way anywhere else, and neither have I. This nomenclature is very particular to this pattern book. So that's kind of another way. It's like assembly language. It's particular to this specific processor architecture or knitting pattern book. So it's not very portable. I can't just give this to another knitter and expect them to be able to run this and execute this. Also notice no longer a one-to-one match with the output. You know, the chart kind of makes a picture, but that's mostly because they put those dark lines on it. Like without that, it'd be really difficult to tell if what you were knitting actually looked correct. So modern knitting charts try to balance abstraction and portability with faithfulness to the output. You know, we still don't have a single worldwide standard, but we're kind of getting there, and these ones are widely used. So those big circles, for example, they're yarn overs, or they look like the holes that you create. Decreases, 2-to-1 decreases, are indicated by the forwards and backwards slashes, because when you create them, they create a visual lean to the left or the right. And a 3-to-1 centered decrease, that's that sort of bird foot, 3 chicken foot thing. So it conveys a lot more information. I mean, between the symbols and the colored lines, you got like 9 pieces of information in a very compact space. But some knitters think we can take this even further. The problem, they say, is that grid. So let's go back to that feather and fan again. And you see how it undulates, you know? When you create the increases and decreases, it creates curves. And you don't get that in an orthogonal grid. You get this, which is concise, it's readable, it adheres to the standard, but it doesn't look like the end product. So a new syntax has been proposed, stitch maps. Stitch maps are basically the 4th generation of knitting chart language, and they look like this. So the idea is that stitch maps lets you see how part of a stitch pattern fit together, not just the sequence of stitches in any given row, but the way those rows affect subsequent rows, or clock cycles, if you will. And the really cool thing is that stitch maps are compiled from a domain-specific language called knitspeak. So you can go to the stitchmaps.com website, that address there, and enter a stitch pattern like this, which looks basically like a normal knitting pattern, and it will compile that and turn it into a stitch map visualization that looks like this, which is really cool. I mean, I love that. I would do all my patterns this way. And as with most things, the Japanese are way ahead of us. You know, I mentioned cultural affiliation. They use symbols, graphs, and schematics in all of their knitting and crochet patterns. And it's great. It makes them extremely portable. I can go to Kinokuniya and buy a Japanese knitting magazine, and I can work from it, even if you don't speak Japanese. But sadly, most Western knitters prefer text patterns, even though they are incredibly inefficient. I'm actually going to show you here the first textual knitting pattern ever published in English in 1655. This is the order How to Knit a Hose, which is how to knit a sock. And it looks impenetrable, and it is. But if you're a knitter, it kind of sort of makes some kind of sense. Like, I read it, and my brain can kind of start translating it. But the UX is terrible. I mean, you can't see the parts of the pattern. It's vague. It's hard to follow. I actually looked this pattern up on Ravelry.com. Of the 6.5 million knitters on there, exactly 1 person has actually knitted these socks. So wherever he or she is, Des in Canada, I salute you. But thankfully, as with charts, text patterns evolved over the years to become more standardized, more abstracted, and more concise. So this is from 1846's The Knitter's Friend. It's a lot more readable than the last one. Cast on row, clearly marked, each row's instructions set out. It's even got some abbreviations in there to make things concise, which is great. But what's not great is that the white space and indenting is kind of all over the place. And the abbreviations aren't just non-intuitive, they're misleading. You know, the P3 here doesn't mean purl 3. It actually means a plain stitch or loop, which nowadays we call a knit stitch. And the B, which I thought was a typo at first, actually means a back-ribbed seam or purl stitch. So it's a purl. So it's exactly backwards of what I would have expected. This is like the whole big endian, little endian thing, you know? If I executed this pattern without checking the intended scheme, I would end up with the exact reversed output that I was intended to get. So this is a modern knitting pattern. This is sort of like a third generation knitting pattern language. It's very clear and easy to follow. It's got consistent syntax and white space, even uses fairly standard abbreviations, has modules, tells you how to swap them in and out. So it's pretty good. But it's still got those ugly switch statements with 9 different sizes, and there are a lot of them. So again, some knitters think we can do better. KnitML is an open source project. It really is, with a goal to promote a new international standard and intermediate format for knitting pattern expression. The KnitML user guide states outright that knitting patterns are algorithms as much as they are documents. Consequently, it's important that a computer be able to understand the algorithm so that it can make decisions. So formalizing the knitting pattern into an algorithm in this way allows for all sorts of useful operations. For example, instead of having to circle my size out of all those switch statements, I could generate a pattern which has just the size I want. I could, since I like charts better than text, I could have it in charts instead of text. I could put it in my preferred language with my preferred abbreviations, whether you use English or metric measurements, up to you. It could even compute out those occasionally mathematically complex instructions like increase 37 stitches over 171. And the system would have advantages for designers too. I mean, they could write patterns in the way that made the most sense to them with the knowledge that their customers would be able to download it in the way that made them happy. And what's more important, they could use tests to check for errors. So many knitting patterns have errors. And they could even use a visualizer to preview the output of the pattern. So this is what KnitML looks like. It's not particularly compact, nor does it bear much resemblance to a traditional knitting pattern. But remember, this is just an intermediate format created for the sole purpose of software pattern exchange and transformation. It's not expected that human beings would ever actually touch this stuff. Instead, the project provides a pattern authoring tool called KnittingEL, which stands for Knitting Expression Language. This is a simpler way for designers to express a knitting pattern. It looks kind of more like a published pattern, sort of. The project provides Java-based software to convert KnittingEL patterns to KnitML, and then KnitML can then be passed on to supporting software, as I said, like validators, renderers, and visualizers. For example, here's an example of an open source visualizer called Knitter, which processes a KnitML pattern and produces a 3-dimensional model of the resulting knitted fabric. You can even stretch the fabric and see how it'll behave. This sort of thing wouldn't be possible without a new spec. But I know, standing in front of an audience of engineers, what they think as soon as they hear me say new standard, you know, the joke. And to an extent, that's pretty much true, you know. After a flurry of initial development, KnitML has not taken over the knitting world in the way that I would have preferred. It's kind of languished, and people are still publishing patterns in the old stupid way on paper and ink, filled with redundant information in ways I don't like, with errors. But thankfully, the world of open source knitting is a lot bigger than just KnitML. So if you don't believe me, go to GitHub tonight, type in knitting. Actually, the screenshot's a bit old. There's probably more by now. There are hundreds of repos that you can play with. There are Go language implementations of knitting pattern parsers. There are custom row counters for your Pebble watch. Apps for turning JPEGs into knitting charts. I like this one. This is the source code to a knitting Ipsum generator for your next knitting blog. Instructions for wiring your own Stitcher row counter, which only slightly look like a bomb. This is a fun one. This is from knitty.com. This is a pattern for a knitted bag. So you knit the bag, you felt it. Then you use a LilyPad Arduino, a conductive thread, and LEDs to wire it up. So the idea is you carry your knitting around in your bag, you program the LilyPad Arduino, and actually when you press the button, the lights twinkle with the stitches for the next row of the pattern that you're knitting. Very clever. Have you guys heard of Mariko Kosaka? She's amazing. She created a simple pattern generator called 64 Stitches that lets you type in a pattern in really simple syntax and see what it'll look like when it's repeated. But more importantly, she did an amazing talk at JSConf last year called Knitting for JavaScripters. It's on YouTube if you want to check it out. I am just in her shadow, really. And in it, she talks about, she goes pretty deep into one of the most popular crossover knitting and tech activities right now, which is hacking old knitting machines from the 70s and 80s. So these are very popular. Brother made them. Like, they were very big back then. That guy's loving this. And you can pick one up on eBay pretty cheap. So some of them actually used punch cards to input patterns. Some of them had hundreds of patterns built in, you know, like they were computerized. Occasionally they'd have a UI with buttons so that you could pixel by pixel pick out a new pattern. A couple of them had floppy drives, not many. So hacking them basically involves making your own serial cable and then writing software to transfer new custom designs to the machines. And people are putting these to some very cool and very weird uses. So on the cool side, the neuro-knitting project plotted brainwave activity into a knitting pattern. So they used a wearable EEG to record users' affective states while listening to Bach's Goldberg variation, and then knitted that into a scarf on a hack knitting machine. So that is the guy's brainwave as he listened to the music. Now on the weird side, and warning, nightmare fuel, you get artists. So you get artists. This is Andrew Salamone and his machine-knit identity-preserving bitmap balaclava. He photoshopped images from his head, from every angle, into a single rectangular bitmap, knitted it on a hack knitting machine, and sewed it into a balaclava, because why not? My favorite knitting tech project of the last few years was KnitYak. So Fabienne Serrière, she's FBZ on Twitter, she's using a hacked industrial knitting machine in a shipping container in Portland, because, of course, to knit provably unique scarves using elementary cellular automata. So as a backer of this project, very soon I will be able to select my colors, my starting row, and the particular rule that I want to knit into my unique scarf. And that kind of brings me to my last topic, which is knitting is computation. And I'm going to start here with a massive caveat that I am a much better knitter than I am a computer scientist. But I've been reading this book lately, Code, The Hidden Language of Computer Hardware and Software by Charles Petzold. Anybody else read this? It's really good if you've maybe come not from a CS degree into this industry and you kind of have the suspicion you don't really know how computers work. And I suspect that Venn diagram is actually big. So you want to read this book. And he explains how computers work, starting from just very simple circuits and building all the way up through Boolean logic and logic gates to create a simple binary calculator onto processor architectures and then programming languages. And it's just really cool. And it got me, you know, as I'm knitting, as I'm reading this, as I'm thinking, it got me thinking about this in a sort of philosophical way. And you know, in this talk, I've mentioned a couple times, I've joked about the human brain being the CPU and the knitting computer. And I kind of thought, well, how much of a joke is that? You know, could knitting really be seen as a type of computation? So I said this to my husband, and he went, well, it's not. And his view was that knitting patterns are more like markup language, you know, like say HTML, that they kind of, you know, define a markup define the way that the output is meant to look, and then the human being is just like a rendering engine that puts it together. And it kind of makes sense. I mean, that KnitML project is using XML anyway. But I don't really like that metaphor, you know, I think it has its limits. So, you know, as a developer, you want a web browser to render all your HTML in the same way, preferably identical, but knitters don't churn out identical projects even when they knit from the same patterns. And knitting patterns do allow for more complex logic than simple, you know, simple HTML or CSS. They have branching, they have nested loops, subroutines, coroutines. So to an advanced knitter, when you're working on a complicated project, it feels more like executing a program than just running markup, rendering HTML. Okay, so take it for the moment that knitting patterns are a programming language. So what else would we need for a knitting computer? Well, we need a CPU, which we've already sort of identified as the human being, which is responsible for both fetching instructions and writing the data, which of course is just knitting the stitches using data objects, which happen to be called needles. The RAM would be the live stitches on the needles, which are eventually written and saved to external storage, which is the thing that you're knitting. Free memory, you want free memory? Got a whole big ball of yarn, and the knitted object itself actually doubles as the output device. Did I just compare knitting to von Neumann architecture? I think I did. So if you're interested in taking this further, and like I said, I'm still a noob at this stuff, there's a really fantastic blog post called Towards a Computational Model of Knitting, which covers things like the 4 clock cycles required by the default stitch processing operation, and how regular knitting needles are like a last in, first out stack, but double points are a first in, first out deck. It's all very cool. So knitting, I mean, even said, that still has some limitations, you know. when you knit, the memory isn't really random access. It's written entirely sequentially. You know, I started thinking about Turing machines, and with a Turing machine, it's essential that you be able to go backwards as well as forwards, and you can't do that in knitting. If you make a mistake, you pretty much have to pull it undone. And most critically, like 99.99% of knitting patterns, the output is predetermined. You know, there's not really any real conditional branching. All you're doing is writing. And so nothing you do in one row is actually reliant on what you did in the previous one. So you don't compute, you don't arrive at an end result. But I realize not in every case. You know, I talked about those scarves that KnitYak is producing using cellular automata. Those can be knitted. So I could start off with a one-dimensional pattern of ones and zeros, whether those are knits and purls or two different colors. And I can use a rule, and that pattern can evolve over time according to that rule. So this is an example of Rule 110. And as I'm sure some of you know, in the year 2000, Matthew Cook published a proof that Rule 110 is Turing complete and is capable of universal computation. So given an infinitely long ball of wool, I can simulate any Turing machine and by extension the computational aspects of any possible real-world computer, which I find pretty mind-blowing. So on that note, you can ask me some questions, and then we can all go for a beer. Thank you.